In the previous unit, we finished deriving an ordinary differential equation for the flow, considering it to be a quasi-one-dimensional flow with heat addition. In this unit, we're going to take a look at that one-dimensional Mach number-based equation, understand what it's telling us, solve it, and then interpret the results of that solution. Let's pick up from where we left off in the previous unit. We went ahead and combined the momentum equation along with the energy equation and all those other assumptions we've made so far, and cast it, after a lot of algebraic manipulations, into a Mach number-based equation, which is this equation right here. Now, as you can see, this equation has two distinct parts. On the left-hand side, everything is expressed in terms of the Mach number as well as the ratio of specific heats gamma. On the right-hand side, everything is expressed in terms of the total temperature T0. So let's first think about what this equation is telling us before we proceed to solving it. As we did with the flow with friction, we've again identified that there is this factor on the left-hand side, which is purely a function of Mach number and gamma. And so I'm just going to highlight it so we can look at what that factor is going to look like under different scenarios. Now, before we do that, let's take a look at the right-hand side, which is dT0 over T0. Now, we understand that we want to add heat to the flow, which is what the combustor is designed to do. And if we do that, dT0 is going to increase. In other words, dT0 over T0 is going to be a positive number always in the combustor. Now, with that in mind, let's look at what this highlighted factor, which is in terms of the Mach number, going to do under different scenarios. Okay, first let's consider the case of subsonic flow when the Mach number m is less than 1. Now, if that is the case, I'm going to examine first the denominator and figure out if the denominator is going to be a positive or a negative number. So let's take a look at the first expression there, which is 1 plus gamma minus 1 over 2 times m square. Now, we know that gamma, which is the ratio of specific heats, is always greater than 1 in the combustor. If that is the case, then the first expression there, 1 plus gamma minus 1 over 2 multiplied by m square, is always going to be a positive number. Likewise, if you look at the next expression, which is 1 plus gamma m square, that's also a positive number. So essentially, this means that when the flow is subsonic or supersonic, it doesn't matter, always the denominator is going to be a positive number. Okay, so now let's take a look at the numerator, 1 minus m squared. Clearly, when the flow is subsonic or m is less than 1, we can see that 1 minus m squared is going to be greater than 0. Okay, or the factor overall, the highlighted Mach number based factor, is going to be greater than 0. All right. So we just said in the combustor what we want to do is add heat. So in the case of heat addition or dT not being positive, we will find that for this equation to make sense, that is, on the right hand side you have a positive number, the left hand side also needs to be a positive number, which will then mean that dm square needs to be a positive number because we just said the factor is positive based on our analysis of the numerator and denominator. Now in the event, okay, we're not going to really be interested in this course or hypersonics course, but in the event that you want to cool the flow, then the opposite will happen. That is, because the factor is going to be positive since the Mach number is subsonic, and because our right hand side now dT0 is going to be negative because of the cooling, it will imply that the Mach number dm square will also be negative. Or in other words, in the case of heat addition of subsonic flow, the flow will accelerate. In the case of heat removal or cooling of a subsonic flow, the flow will decelerate. And again, let me just emphasize that in our course, we'll really be interested only in the heat addition, but for the sake of completeness, we'll look at both scenarios. Now let's move on to supersonic flow, or the case when Mach number is greater than 1. This is really the kind of flows that we're interested in a scramjet engine, in which the flow comes into the combustor after the inlet compression and is still supersonic. Okay, so let's do the same analysis that we did for the subsonic flow. In the case that the Mach number is greater than 1, this numerator 1 minus m squared is going to be negative, which essentially means the whole factor, which is in terms of the Mach number, is going to be negative or less than 0. All right. Now, in the case that we're adding heat, which is what the combustor is designed to do, or dT0, the right-hand side, is going to be a positive number. The overall left-hand side now needs to be a positive number. We just said that the factor is negative, which means dm squared needs to be negative. In other words, when you add heat to a supersonic flow, you're going to slow down the flow or decelerate it. Like we did before, Let's just complete the argument in the case of cooling, which is not of particular interest to what we are aiming to do in this course. But if we take the supersonic flow and remove heat from it, we can find again that the right hand side dt naught is going to be less than 0 because of the cooling. And because the factor is always negative, then dm square needs to become positive so that the overall left hand side can be negative. In other words, if you take supersonic flow and cool it, you're going to accelerate the flow. So we just understood qualitatively by using this one-dimensional, quasi-one-dimensional model in which we derived an ordinary differential equation in terms of the Mach number. Just by qualitative arguments, we've kind of understood what heat addition is going to do to subsonic and supersonic flow, and likewise what cooling is going to do to subsonic and supersonic flow. Now, we have not quantified exactly how much acceleration or how much deceleration the flow will experience, or what will be the point up to which you can accelerate. Those are things that we can consider only after we solve this equation. Therefore, let's go ahead and do that. Let's take up this ordinary differential equation, which is nicely separated out in variables, all the Mach number expressions on one side, the dt naught over t naught, or the temperature expression on the right hand side. Let's do what we did with the case of the frictional flow. That is, we applied the method of partial fractions and integrated in that scenario. We're going to do the same thing here. Once we do that, we get this final solution, which is an expression in terms of still the Mach number on the left hand side, but a natural logarithm function. Likewise, on the right hand side, we have natural logarithm in terms of T naught, or the total temperature. Again, we've not specified where we start or end, but let's assume that we start at location 1 with the Mach numbers m1, and as we proceed downstream to different locations, let's say location 2 somewhere downstream, the Mach number will be m2, and corresponding to that you'll have T naught 2. Now that we have the solution of the differential equation after integrating it using the method of partial fractions, in order to better physically understand what this complicated expression is telling us, let us first define the Rayleigh function Rm as a function of Mach number, which is exactly everything that was inside the logarithmic function here on the left. Once we have the Rayleigh function Rm defined, we can then go ahead and plot that versus the Mach number, which is the graph shown on the right, and also simplify the expression for the final solution in terms of the Rayleigh function as R at m2, or the Mach number at the second downstream location, divided by R at m1, or the inlet location, should be equal to T naught 2, which is the total temperature at the downstream location, divided by T naught 1, total temperature at the starting inlet location. Now let's take a look at the graph on the right. Let's assume that the flow enters the combustor supersonic, or in other words, let's say that our inlet Mach number m1 is on the supersonic branch indicated by the yellow point here. Now let's look at the final solution and realize that when we have flow with heat addition, this equation needs to be valid. Or in other words, since we are adding heat, T naught 2 is going to be greater than T naught 1, which means the right hand side is going to be greater than 1. Therefore, the left hand side also needs to be greater than 1, implying that the value of the Rayleigh function at m2 needs to be greater than the value of Rayleigh function at m1. So just taking a look at this curve here, we realize that if we start at location m1, or Mach number m1, and the value of the Rayleigh function corresponding to that is somewhere here, in order for the Rayleigh function value at the downstream Mach number to be greater than the value at m1, we need that the Mach number at the downstream location has to be along this branch. In other words, when you add heat to the supersonic flow, you'll find that m2 will need to be less than m1 so that the ratio of the Rayleigh function can be greater than 1. And of course, as you start adding more and more heat and the flow goes more downstream, we'll find that eventually the flow will have to choke and reach Mach number equals 1, which is the highest value for the Rayleigh function. Now let's examine what happens if we start out with subsonic flow, or in other words, m1 is on the subsonic branch indicated by the red dot here. Again, the same thing needs to hold true, that is, when you have subsonic flow and you're adding heat, T naught 2 over T naught 1 is again going to be greater than 1 as per the earlier arguments, which means the value of Rayleigh function Rm2 needs to be greater than Rm1 again. And looking at the shape of this curve, it's clear that that can only happen in the branch between the red and the green dot, which is here. Therefore, for the subsonic flow, when we add heat, we again find that the flow will accelerate and reach Mach 1 as the maximum value that it can reach. So, surprisingly, the case of heat addition also yields us the same results as the case with friction. That is, when you add heat to the flow, whether you're supersonic or subsonic, eventually the flow will reach Mach 1 and choke. In the case of supersonic flow, the flow was decelerated from the supersonic Mach number m1 eventually to the Mach 1 here. And in the case of subsonic flow, we started with subsonic m1, which then choked, reaching m equals 1. Just to finish the arguments that we've been making about flow with heat addition, we can also examine flow which is cooled, which is not precluded in this formulation in any means. So, for example, if we start out at m1 and cool the flow, we would realize that T02 over T01 will be less than 1 in that case, which means Rm2 over Rm1 has to be less than 1, and that will happen in this branch. Or to change the argument over, we can say if we are mildly supersonic, that is a little bit over Mach 1, and we start cooling the flow, we'll find that the flow will accelerate with greater and greater Mach numbers. The same argument can be made if we are mildly, or we are just about Mach 1 but still on the subsonic side, and start cooling the flow, we'll again find by the same arguments that the flow will decelerate. Now that we've examined the solution and understood the influence of heat addition on compressible flow, we saw that whether we start with subsonic or supersonic flow, if we continue to add heat, we will choke the flow to Mach 1. Now that we know that, let's make use of that idea to express all the flow parameters in terms of the starting Mach number m and ratio it to the downstream location where it's going to eventually choke. Like we did with the case with friction, we're going to denote all the flow parameters at the choking point with a star. So let's start with the total temperature ratio T0 over T0 star, which is nothing but the Rayleigh function that we defined previously at m over m star, knowing that m star is actually 1. So writing out the Rayleigh function, we get this expression, which will be further simplified as T0 over T0 star equals an expression that's purely in terms of the Mach number and the ratio of specific heats gamma. Next, let's look at the temperature ratio T over T star. Before proceeding, we can multiply and divide by T0 in the numerator, multiply and divide by T0 star in the denominator, and we already have expressions from isentropic relationships for T over T0 or T0 over T. Similarly, we could have an expression for T0 star over T star, and we just developed an expression for T0 over T0 star above here, and we just need to plug in all of that and write this out as this expression in terms of the Mach number times T0 over T0 star. Once we substitute for T0 over T0 star, we're going to get T over T star equals gamma plus 1 m divided by 1 plus gamma m square, the whole square. Now I've not shown all the simplifying steps. I assume you'll be able to work it out by yourself. Let's proceed to develop an expression for the pressure ratio. To do that, let's start first with the momentum balance equation in the differential form, which was dp plus rho u du equals 0, and integrate that from the current location where we are at the inlet to the downstream location where the flow will choke, which is the star location. So when we do that, we get p plus rho u square equals p star plus rho star u star square. Now we know that we could do this integration only because the rho u was a constant, therefore this expression could be integrated directly. Next, let's use the equation of state P equals rho times R sub g times T and substitute in here for the density rho from that expression. When we do that, we would first get u square times P over R sub g times T, and we notice that I've already multiplied by gamma over gamma, and again we do this because we have identified that gamma times R sub g times T is a square. Doing the same manipulation in this square, on this side, on the right hand side, we would get a star the whole square, which is the speed of sound. Alright, once we have u square over a square, that's nothing but m square, or the Mach number square. Likewise here, this will be m star square. Using that and rearranging terms, we'll then find that p over p star can be expressed as gamma plus 1 by 1 plus gamma m square, in which I've implicitly used the assumption that m star, which would have come out here, equals 1 at the choking location. Proceeding to the total pressure ratio, P naught over P naught star, we can again do an algebraic manipulation of multiplying divide by pressure in the numerator, multiply and divide by P star in the denominator, and then try to use expressions for P naught over P from the isentropic flow relations, and P over P star, which we just developed here, and express the whole expression of P naught over P naught star in terms of the Mach number. Density ratio can also be written out as rho over rho star equals, once we use the equation of state, P over P star times T star over T, and since we already have expressions for P over P star and T over T star from the previous slide, we get 1 plus gamma m squared divided by gamma plus 1 m squared equals rho over rho star. Now that we've developed relationships for all the flow parameters to the choked location, let's make some plots and look at what they're telling us. The blue line here is the ratio of the total pressure P naught to P naught star, and the black line is the ratio of total temperature T naught to T naught star. Now we know that in the scramjet engine, the flow is going to enter the combustor with a supersonic Mach number m1, which could be anywhere between 2 to 3 or even beyond that. And we're attempting to add heat into that flow. From our analysis of the flow with heat addition, we know that when we do that, the flow will decelerate, and effectively we will be traversing the black line here, meaning the total temperature of the flow is going to increase. Unfortunately, we see that when that happens, simultaneously the total pressure P naught is going to be dropping. Now ideally we want a high pressure, high temperature gas to leave our combustor so that we can extract useful work from it and derive thrust. Now if the total pressure is going to drop as we add more and more heat, even though we gain benefit in terms of the total temperature increasing, the drop in total pressure might be hurtful to the performance of the engine. Therefore, the amount of heat that can be added will depend very much on the design condition for which the combustor is being designed for. Now this is something to keep in mind, and we'll show that we're going to be focused on what's happening in the combustor in this region, mindful of the fact that while the total temperature is increasing, the total pressure is actually decreasing. Having understood that adding heat to the flow is going to cause the stagnation temperature increase, but unfortunately cause the stagnation pressure to decrease, let us see if there are any other design implications. First, we know from thermodynamics that more heat addition will increase the thrust as well as improve the efficiency. However, we also know that heat addition on the supersonic branch will cause the Mach number to reduce and eventually cause the flow to choke, reaching Mach number equals 1. Therefore, the main design implication that excess heat addition poses to our combustor and the engine on a whole is that the engine can unstart because of the flow choking. Therefore, the total heat that is added is going to be a compromise between performance and the stability of the engine. We also know that excess heat addition will cause the pressure to drop, the stagnation pressure to drop.